everyone, we are from Group B. We'll be present our practical one, which is topographic surveying by using automation method. This practical work 1 was conducted on 20 November 2021 and submit on 2nd December 2021. The durations of this practical work 1 is only 2 weeks. We were asked to running a traverse network. Horizontal control includes connections for azimuth connections and control. Second, we runs a leveling network, which is vertical control for height transfer to the control point. Third, conducts detailed surveys to provide information on many aspects of the design and implementations of engineering projects. Perform data processing using civil design and survey software, which is CDS software. Perform data editing using AutoCAD software. Produce detail elevations and site plan in accordance with the standards of licensed land surveyors. While completing this practical work 1, and we were monitored by our lecturer, Encik Muhammad Firdaus bin Aminuddin. With this is to ensure that the work of our group is correct and runs smoothly. Horizontal control surveys coordinate horizontal positional data. This position can be referenced by parallel or plane coordinate axes because they are used as a framework for other surveys. These surveys must be precise and accurate. These surveys provide a network of monument or point on the ground that can be used as the control for any other surveying project, such as a boundary or a construction survey. The advantage of using a horizontal control survey is that the lost monument can be replaced accurately. Surveys can be coordinated. More than one network station can provide a check to the work, and a reduction in the cost of the project can be achieved. Most horizontal should and will be connected to the control network. A vertical control survey is performed for accurately determining the autometric height, which is elevations of permanent monuments to be used as benchmark for lower quality labeling. Spirit labeling is the usual method of carrying elevations across the country from sea level tidal gauge. However, global positioning system GPS can be used indirectly but with the less accuracy. Height measurement from the ellipsoid as opposed to the sea level gauge can be determined very accurately with GPS and only with GPS. Trigonometric labeling with a data station is not acceptable for vertical control work. The objective of this practical one, which is to expose students with the automation survey concept to conduct topographic surveying. Second, to process data and to produce topographic plan using civil design and survey, which is CDS and AutoCAD software.
Next, I will continue present about work procedures for differential field test and two-pack test. DFT is implemented at work locations when daily checks have a distance difference of more than 10 mm and when each time starting a new survey job. First, what we need to do is plan pickets A and B with not less than 60.234 meter. Third, pair the ADM in A and prism in B and measure the distance A to B. Third, plan picket in C is approximately the AB line. The distance picket A to C is 6.718 meter. The distance for picket C to B is 33.516 meter. Switch ADM in C and pair prism in A and B. Measure CA and CB distance. AB distance should be compared to the number of distance CA plus CB. If it is found that the distance exceeds 10 mm, the device test cannot be used. It should be calibration test. And this is the example for measure DFT at fieldbook test.
2 PEG test. Permanent adjustment. All instruments are subject to error of calibration and adjustment. In the case of leveling instrument, the main source of instrumental error is where the line of sight produced by the crosshairs in the telescope is not parallel to the horizontal line of collimation produced by the manufacturer of the instrument. This error is known as collimation error as it affects the line of collimation. The test that we undertake to determine the amount of error and then eliminate it from our measurement is known as the 2-PEG test. This is example of 2-PEG test, 2PT. The 2-PEG test is used to determine if the line of sight of the telescope is exactly parallel to the bubble tube. This is one of the most important prototypes of a level and rigor to be checked periodically. Below are the steps to carry out 2-PEG tests. First, set 2 points with 40 meters. Number 2, set up the level halfway between the 2 points at point C as illustrated in figure above. Number 3, the staff reading at point A and B are taken. The bubbles need to be adjusted each time before the readings. Number 4, the level is then moved to point C and reading are taken to staff at point B and A. Number 5, the true difference in elevation between point A and B is computed from the 2 readings obtained from the first setup, A1 to B1. And lastly, the elevation difference of the second setup is computed A2 to B2. If the plane of sight is truly horizontal, the elevation difference of the second set is equal to the true difference in elevation A1 to B1, A2 to B2. Set the distance of AC, CB, BD. If the difference between AC, E, so the difference of CB, BD, E, thus the distance of DA, 3E. Refer to the following table. Instrument at station C, D. Staff reading at A, A1 equal 3.75, A2 equal 7.86. For B, B1 equal 4.25. For B2 equal 6.36. The difference A equal 0.5 unit higher than B, actually different. B equal 1.5 unit higher than A, appearance different. Note, if A2 minus B2, A1 minus B1, so adjustment must be set up. With instrument at D actually reading A2 equal A plus 3E, with instrument at D actually reading A2 equal A plus 3E. Thus, reading at A equal A2 minus 3E, actual reading B2 equal B plus E. Thus, reading at B equal B2 minus E. Hence, actual correction equal actual reading at A minus actual reading at B. A2 minus 3E minus B2 minus E. 7.86 minus 3e minus 6.36 minus e equal 1.5 minus 2e, but two different equal a1 minus b1. 3.75 minus 425 equal negative 0.5. Negative 0.5 equal 105 minus 2e. 2e equal 2, e equal 1 meter distance. With instrument at D, actual reading at A. A2 equals 7.86 minus 3 equal 4.86. Actual reading at B. B2 equals 6.36 minus 1 equal 5.36.
Control survey horizontal. Horizontal control surveys coordinate horizontal positional data. This position can be referenced by parallels or plane coordinate axes. Because they are used as a framework for other surveys, these surveys must be precise and accurate. These surveys provide a network of monuments or points on the ground that can be used as the control for any other surveying project, such as a boundary or construction survey. The advantage of using a horizontal control survey are the lost monuments can be replaced accurately, surveys can be coordinated, more than one network station can be provide a check to the work, and a reduction in the cost of the project can be achieved. Most horizontals should and will be connected to the control network. Next is vertical. A vertical control survey is performed for accurately determining the orthometric height elevation of permanent monuments to be used as benchmark for lower quality leveling. Spirit leveling is the usual method of carrying elevation across the country from sea level, tidal gauges. However, global positioning system GPS can be used indirectly but with less accuracy. Height measurement from the ellipsoid as opposed to the sea level joint can be determined very accurately with GPS and only with GPS. Trigonometric leveling with a total station is not acceptable for vertical control work. Traversing in surveying method. Number 1. Conduct a field reconnaissance at given area determined by lecturer. Number 2. Start working by using compass to get datum value. Number 3. Distance between stations must be more than 30 meters and less than 80 meters. Number 4. The traverse route must consist minimum of 4 stations. Number 5. Set up the tripod and total station instrument at station point. Number 6. Level the instrument through the circle bubble is located at the center. Number 7. Set up first the prism as back station and second prism as forward station. Number 8. Focus and target prism. Number 9. Measure bearing, horizontal distance, vertical angle, and slope distance. Number 10. Transit total station to forward and target the prism foci. Number 11. Measure bearing, horizontal distance, vertical angles, and slope distance. Number 12. Repeat above steps to complete the traverse. Each group must conduct first-class traverse, complete with field book traverse adjustment and accuracy calculation. The methods are: Number 1. Mark point A, B, C, and D in the ground with pegs as shown in diagram 2.0. Number 2. Set up the leveling instrument at point C and read staff readings at point A and B. The reading will mark as A1 and B1. Number 3. Then set up leveling instrument at point D and again take the staff readings at point A and B. The readings will mark as A2 and B2. Number 4. Calculate the height differences from the staff readings using the formula A1 minus B1 equal to A2 minus B2. Number 5. If the height differences are not the same, there is collimation, error, and adjustment to the instrument indeed. Conduct close and series leveling survey. Number 1. Locate the TBM or BM for starting point. This will be the starting station and first backside. Number 2. Set up the leveling instrument at an appropriate position about 30 to 50 meters from the TBM. At the meantime, a staff man will hold a leveling staff vertically with the aid of a staff bubble on the BM. The first reading taken on this staff is known as the BS and booked accordingly as shown in diagram. Next, another staffman shall locate the forward point known as the change point. This is to eliminate collimation error, if any. Number 4. The surveyor will then focus to the forward staff held vertically at the change point. This is the first change point. To read the staff reading, which is known as the foresight, and to be booked. Number 5. At the meantime, while reading the foresight, the staffman at TBM shall move to find the next change point. Number 6. The instrument man shall move to instrument station 2. Make sure the BS distance is equal to FS distance. To make the BS and FS reading, an intermediate side may be taken. The last one, the process shall be repeated until the next nearest TBM is reached. If another TBM is reached, the leveling circuit are known as the series leveling. If leveling circuit reach back to the starting TBM, the leveling circuit is known as closed leveling.
Topography survey using automation method. Set up and collection of survey data. 1. Press button on and press menu. 2. Press F1 data collect. 3. Press F1 input again if want to create new job and press F4 enter when finished. 4. In data collection screen, press F1 OCC PTH input. 5. Insert all of data PTH ID INSHT by pressing F1 input and press F4 or CNEH. 6. Press FE and EZ. 7. Input the value for N, noting, E, ST, and Z evaluation by pressing F1 input and press F4 enter after each entry. 8. Press ESC to go to the next screen after input the Z evaluation value. 9. Press F2 backside. 10. Input for backside P-code and RHT by pressing F1 input and press F4 backside. 11. Press FE horizontal. 12. Press F1 input for input the backside bearing and press F4 enter. 13. Carefully aim instrument at center of the prism. 14. Press FE measure for the distance value. 15. Press FE, FS or SS for collecting survey data. 16. Input data for PTH, PT code, and RTH by pressing F1 input and press FE measure when aiming to count 17. Then press FE and EZ. 18. The beep sound means the point has been taken. The staff can now be moved to the next point. If you can need to change the point cloud and prism height for particular survey point, this can be done by pressing the F1 input and F4 enter and press FE measure. Next, download the survey data. 1. Connect the station to computer via cable and turn power on. 2. Press menu. 3. Press F3, memory MGR. 4. Press F4 twice. 5. Press F1 data transfer. 6. Press F1 send data. 7. Press F1 measure data. 8. Select a file by pressing F2 list and use up and down scroll key to select job for download and press F4 enter. Number 9. Press FE yes to send the measure data. Then when download is complete, turn total station off and disconnect. Prevent for data download. Connect the total station to your computer or laptop to obtain the survey data by connecting the cable for communicating an external instrument by series signal connector or USB from total station to computer or laptop.
Data processing. After completing the data transfer from total station of the survey work to the computer or laptop, the data need to be processed using specific software, which is civil design and survey software. Before conducting the processing work, CDS software is needed to be downloaded to your computer or laptop from ForSoft website. Creating a new survey job. To create a new survey job, pull down the title menu and select New or click on New Job icon in toolbar. After that, name the job as based on preference. We need it as Amali work, then click open. Once you have saved the new job, your screen will appear as seen below, and you will see that the new job has appeared with a blank screen. To recognize the selected job, the screen appears to have the job title on the top bar as shown in the below picture. Next is transfer raw data from total station. In this part, it shows all the procedure to download measurement data from a data recorder such as total station. This is the crucial part because if the raw data are not downloaded properly, the next chapter cannot be done. Communicating with total station. There are three components involved, which are computer to CDS software install, cable for communicating and external instruments by serial signal connector or USB, total station to data recorder. The total station must be connected with computer by using cable. Next is 3.2 Total Station Download Parameter Setting. The menu for setting parameter for data communication is different for each total station available in the market such as Topcon, Leica, Nokia, Nikon, and so on. In this training manual, the topography data has been collected using the Topcon GTS 230N series model. The basic theory is same, but the menu arrangement is different between total station brands. The parameter must be same with the communication in setting in the CDS software. And this is item of the parameter. The item should be set as follows. Baud rate is 9600, for data bits is 8, for stop bits is 2, for parity is none, and for flow control is byline then wait. And this is for procedure to set the parameter. Next is 3.3 CDS software download parameter setting. Pull down entry menu, select on data collectors menu and click on collect raw data from data collector. The terminal window untitled columns 32 will appear. Next, pull down setting menu and click on communication in. enter the required information in the input communication. Please ensure the parameter setting is same with total station. After all the information included, just click OK. Next, 3.4 Raw data download procedures. There are two parts involved in this step, which are CDS software and total station. First, hit the transfer button in the CDS software before push transfer button at total station. For CDS software, from terminal window Untitled Comms 32, pull down transfer menu, then click on data to computer. As you can see, for total station, just sending a measure data file. For step 7, select the project by entering its names or press F2 or list to choose the file. To cancel the sending, press the F4 or stop key. If all the settings are correct, the terminal window Untitled Comms 32 will appear. After finish downloading, press Escape keyboard ESC and save the data as save it with file name raw. Then, to import raw data to a CDS Stadia format, just pull down entry menu, select on data collectors menu and click on import raw data. Import raw data screen will appear. There are many types of total session brands available to choose. Select Topcon as the total session brand and FC5, GTS6 as GTS 239 and raw data format. Click on browse to locate the raw file. This will be pop up on the screen. Choose Amali 1 to proceed and click open. For the second step, just click OK until you see the CDS raw LMP2 and click yes. Stadia file for the job has been created. As you can see in the figure 4.0, the Stadia title at the top of the bar is Stat 1. Training Manual. It means this is the first Stadia file for the project. When you open another Stadia file, it's automatically numbering the Stadia as example, Stadia 2. Training Manual and Stadia 3. Training Manual. Topography Surveying Data Processing. This chapter explains about the procedure to process Stadia file in the order to calculate coordinates and hitch for measurement data. Then the last step is to show the topography data graphically and export into drawing format. First, open the Stadia files. Pull down entry menu and click on Electronic Stadia. Click on Stadia, then click on Browse to locate the Stadia file or click on Open Exciting if the file are already there. Select the previous Stadia file as example, Stat 1 Training Manual, then click on Open. The Stadia file table will appear. As you can see, all the information collected in the field have been recorded properly. Next, entering control points value for datum. To enter the coordinates and hitch value of control points for datum, we need to insert new row before the first station row. To do this, click on the first row. Please make sure the row is highlighted after the click. Then, press the Insert on keyboard to add new row. This new row has been added successfully. To enter the coordinate and hitch of control points, make sure the setting for new row as follows. One type is STN. PT is occupied and backside numbering station for datum. In this job, the station number for occupied station is 101 and backside is 100. For east and north, the coordinates for datum. Hitch for the mean sea level values for the control points. For PC is attribute for the numbering. After finish setting the all data, calculate coordinates and hitch. Click on Option menu and select on Calculate Coordinates to compute all the coordinate and hitch for detailed measurement data. Then pull down option menu. Click on Show Coordinates, then coordinate and H for each data are shown as below. After all coordinates and H for measurement data has been calculated, we need to show topography details graphically. Pull down option menu, click on Store Data in Database. Tick on All, then click on OK. Press on CDS shortcut key Z and E for zoom extend. Below is the result. The data shown in the screen is in point number layers. To change it into another layer, click Layers icon in toolbar. Layers, Modes, Surface Parameters screen will appear. Click Modes Display tab. Tick on Modes and tick on Hitch. This will open layer for Hitch. Last, click on OK. The result as shown in figure 5.0 and 5.1. Next, export to drawing format. The details graphic in CDS can be exported to drawing format. There are several settings of parameter need to be checked through the CDS software. First, pull down File menu and click Plot Parameters. View Print Export Control screen will appear. Click on Sheet Details tab. Enter file name for the drawing such as Vertical Amali 1 and tick on 3D to DWG DXF for the Hitch value. Click on Point Param tab. Untick Use Layer with Point to break each layer into many. Select Point Shape to dot from the list. Tick on Hitch, Point and Chords layer. And change SISA to 3, means the Hitch values in 3 decimal point. Next, click on Point Selection tab, then click again on Reset. This will be appears on the screen. Tick on All, then click OK. Click on String Param type. Tick on Strings, Bearings and Distance, then click OK. To export to WG format, pull down File menu and click on Export DWG. On the Display DWG window, just click OK to produce the topography plan for the project at the AutoCAD software.
Export to DWG format. Pull down File menu, click on Export DWG. On the Display DWG window, tap click OK. Before conducting any drawing in the AutoCAD, set the unit as shown. For the length, type decimal, precision 0.000. Angle, type degree, minute, second. Precision 0 degree, 00 minute, 00 second. Insertion scale, meters, and click direction. Please select North, then click OK on the Direction Control and Drawing Unit tabs. Zoom in on the drawing, right click on the text, click select Similar, and click Properties to shrink the text so that it's all be easier to draw polyline on the points. Simply change the text height based on individual preference. For the result, we can see on the AutoCAD. Constructing frame A3. Rotate the frame at 90 degrees. Scale the frame according to the size of the map. Move the frame to the map and make sure the map is inside the frame. To finish the frame, fill in all the necessary information. Final result, we can see this.
Second, for recommendation and conclusion. In a conclusion, the objective of this laboratory works 1 has been achieved with the guideline given by our lecturer, Sir Muhammad Firdaus bin Aminuddin. From these practical works, we managed to conduct topographic surveying with the automated survey concept. We also able to process data and to produce a topographic plan using Civil Design and Survey (CDS) and AutoCAD software. Topographic surveying encompasses a broad range of surveying and mapping products ranging from aerial mapping to ground and underground survey. Control surveying, like which can cover wide area geodetic survey to construct structure. The following definition from the Flora Administration Code FAC 2003 illustrates. The following definition from the Flora Administrative Code FAC 2003 illustrates how topographic and control surveying fall under the overall surveying and mapping field. A. Surveying and mapping, a process of direct measurement and analysis specially designed to document the extent, the identity, the location, and the dimensional or size of natural or artificial feature on land or in the air, space, or water for the purpose of producing accurate and reliable maps suitable for visualization if needs of such documentation. B. Topographic survey. A survey of selected natural and artificial features of a part of the Earth's surface to determine horizontal and vertical spatial relation.